Long before the moon came to be covered in a solid, cratered crust as we know it today, it was once blanketed in a massive ocean of molten magma. Researchers say the moon was completely molten in its early years, and remained that way until rocks eventually floated to the surface and cooled. But, while a leading theory proposes this process is responsible for the crust's so-called purity, in which much of the surface is composed of a single material, a new study suggests a secondary event may instead have been to blame. In the experiment, the researchers measured how quickly a melt-resistant sphere sunk through the magma. This revealed that the magma melt had a very low viscosity, sitting somewhere between that of olive oil and corn syrup at room temperature. The new analysis suggests the lunar surface may have experienced a crustal overturn at some point in history, when the old mixed crust was replaced with younger hot deposits of the material plagioclase. In the new study, led by the University of Texas at Austin Jackson School of Geosciences, researchers recreated the lunar processes in the lab. Large parts of the moon's crust are composed of 98% of the mineral plagioclase. For the original purity theory to work, the magma ocean would need to have a specific viscosity, or level of gooiness, to allow the mineral to separate from other dense minerals as it rose to the top. According to the team, the moon cooled relatively quickly to create its largely uniform crust. It's fascinating to me that there could be a body as big as the moon that was completely molten, said Nick Dygert, an assistant professor at the University of Tennessee, Knoxville. That we can run these simple experiments in these tiny little capsules here on Earth and make first-order predictions about how such a large body would have evolved is one of the really exciting things about mineral physics. The team flash-melted mineral powders in moon-like proportions, using a high-pressure device at a synchrotron facility. The technique relies on a beam of high-energy X-rays. In the experiment, the researchers measured how quickly a melt-resistant sphere sunk through the magma. Previously, there had not been any laboratory data to support models, said Lin So. This is really the first time we have reliable laboratory experimental results to understand how the moon's crust and interior formed. The leading theories on the moon's formation. Many researchers believe the moon formed after Earth was hit by a planet the size of Mars billions of years ago. This is called the giant impact hypothesis. The hypothesis claims the moon is debris left over following an indirect collision between our planet and an astronomical body approximately 4.5 billion years ago. The colliding body is sometimes called Theia, after the mythical Greek Titan who was the mother of Selene, the goddess of the moon. But one mystery has persisted, revealed by rocks the Apollo astronauts brought back from the moon. Why are the moon and Earth so similar in their composition? We may take its comforting glow for granted, but our moon is an unusual object in the solar system whose origins remain a mystery. There are several theories to explain how it got where it is, and one involves a single, giant impact. Illustrated, several different theories have emerged over the years to explain the similar fingerprints of Earth and the Moon. Perhaps the impact created a huge cloud of debris that mixed thoroughly with the Earth, and then later condensed to form the Moon. Or Theia could have, coincidentally, been isotopically similar to young Earth. A third possibility is that the Moon formed from earthen materials, rather than from Theia, although this would have been a very unusual type of impact. The researchers found that the magma melt had a very low viscosity, sitting somewhere between that of olive oil and corn syrup at room temperature. This, they say, could have allowed the plagioclase to float to the top, but it would also have caused the mineral to mix with the magma, trapping other minerals as the plagioclase crystallized. The findings suggest another process following the initial formation of the crust was responsible for the purity observed in satellites today. This could have been through crustal overturn, or even erosion from asteroids hitting the surface. According to the researcher, the processes that took place relatively quickly on the Moon could shed light on geological processes in other parts of the solar system, and beyond. I view the Moon as a planetary lab, Dygert said. It's so small, and it cooled quickly, and there's no atmosphere or plate tectonics to wipe out the earliest processes of planetary evolution.